Good morning, good afternoon, good evening, everybody. Today's topic is Marc 2019 Feature Pack 1, What's New? Welcome to today's webinar. Today's presenters are Matthew Coakley, who is a product manager for our nonlinear solutions, and myself, Bhumi Gadia. I'm the product marketing manager for MSc Nastran, and Marc. Before we get started, I would like to go over a few technical details about the webinar itself. This webinar will go on for 45 minutes, and then we will reserve 10 minutes at the end of the hour for questions and answers. But again, you can type your questions during the webinar itself in the Q&A panel. And if you're having any technical difficulties, like you are unable to hear us, then you can type in the chat window and we can help you further. So let's get started. I will hand over this part of the presentation to Matthew, and he will get started.
Again, my name is Matt Coakley. I am the product manager for Marc and some of the other nonlinear products in MSc. And I'm excited to show you what we've done in the latest release in Marc 2019 FP1. The agenda is there's 3 categories we're going to go through. We have enhancements that involve the smarter solve. So these tend to be things around performance, robustness, flexibility. These are also enhancements that we find cut across many, or in many cases, all workflows on a solver side. So they're very powerful leverages for everyone to use. We have the parallel sparse iterative solver, user-defined time stepping, enhanced contact parameters, and a point cloud data mapping for global remeshing. It's actually a new default that we'll talk about. And then I will talk about our second area, the GUI improvements we've done. We've made a number of enhancements to the look and feel of Mentat. I think they're very exciting and very helpful for many people, and we're happy to show those to you. And then finally, Bhumi will talk about the use case improvements that we've done, the Vegter anisotropic plasticity yield criterion, the dual frequency induction heating, the single Gauss point tetrahedral Herrmann element, and then the shape memory alloy enhancements. So I'll just go ahead and get started. And as I mentioned, we'll start with the smarter solve. I just want to again reiterate that these are really core solver enhancements, and it's an area that's increasingly important to us. Performance, of course, but as I'll explain, there's 2 sides of performance that we want to improve. Of course, robustness, flexibility, some of the things that we may not have done this release, but we did in the last release with HDF5 in terms of openness, etc. So this is a very broad category, but very beneficial. So I'll start with the parallel sparse iterative solver. So this is solver 2, if you're used to dealing with the unit numbers in the solver. And what we looked at with the iterative solver is we know that it's exceptional when you're solving models with well-conditioned stiff matrices. The speed up is quite good compared to more direct solvers. And so what we have not done until now was really better parallelize it. We did the assembly and recovery operations for the matrix, but we didn't actually address the matrix solver in parallel fully, and we did that at this time. So it's we're gonna see some of the results of that at the use case when we're talking about how we actually tested it. And then we improved the robustness of the solution process, also of solver 2, by adding an option to automatically switch to the multifrontal direct solver, which is solver 8. If the iterative solver cannot converge. And again, this speaks on what we're trying to do in many of these enhancements here. If you can imagine, if you're running a job and then it could not converge in the iterative sense, switching to the multifrontal direct solver is something that we can do to make sure that you're going to get some results out of your run. Actually, the prototypical example many times when you're talking about sparse iterative solvers is large engine blocks. So when I get to showing you some of our test cases, you'll see it. But anytime you have that well-conditioned stiffness matrices, this is going to be a really benefit to you further because now it's parallelized. The implementation. So before I talk too much about the implementation, let me make sure I just turn on my pointer so I can show you where I'm pointing at. We did do some reorganization of the menu for the solvers. We put it into different categories or headers or groups, however you want to call it. And it makes it much easier to look at a list of things and easily separate them out. This is the improvement we've considered doing in many other places with Mentat. So if you do like this, please let us know. We think it really does help with readability of the menus in general. In terms of the sparse iterative solver, you can see we now have the option down at the bottom to turn on multiple threads, and you can then specify the number of threads to get the parallelization, and then a check mark that you can check to switch to the multi-frontal sparse solver when it's not converging with the iterative solver. The only other thing I'll mention about the implementation is to take advantage of this. You will need Marc parallel licenses to run in the parallel. The use case, as I promised in the talking about the enhancement in the beginning, is on a large engine block analysis. You can see here what we tested on is about 1.5 million nodes, 1.6 million elements, so it's a good sized problem. And we actually ran it across 1, 2, 4, and 8 cores, and you can see the speed up factors that we got. It was a really good speed up that we got from using these cores, and we really could use more feedback. Again, if you're running these type of analysis, please let us know how it's working for you. We can definitely continue to work on our performance and parallelization. The next enhancement is one of my favorite enhancements. In fact, I often make the joke that for a product manager, enhancements are a lot like, at first I thought children, but now I actually think it's more like grandchildren, with the product being your child. And you're not supposed to have favorites, but because we're dealing with inanimate objects and enhancements, I can have a favorite, and this is my favorite. I do think that this is something that affects what some people have wanted to do or actually already do, and it really opens up a lot of opportunities for you in terms of having better control. So it's a functionality where it's maybe best described with an image that we'll show at the when we talk about the test cases, some of the test cases we did. But really, in describing it, the way to think about it is we have fixed incrementation, which is you define one increment size based on cutting up the time into even chunks. So every increment is the same size. And then you have adaptive, where you give it a initial increment size, a few other parameters, and you kind of let the program decide. And what we found in our own work in talking to customers is many times there's a middle ground. You want to have perhaps more control that comes with something like fixed, but you do not want to let the computer have full control, sometimes because it will end up in situations where it gets itself in trouble. So the idea here is that with the new functionality, by defining a table, you'll be defining the increment sizes that take place during the analysis, and you have full control of that as a user when you set it up. So you can have small increments at the beginning, larger increments at the end, or any other combination you might want, switching as many times as you want. And it's not a fast switch. You have control over the transition as well. So that'll be, I think, a little more apparent at the end. So I'll go ahead and talk about the values we think this does, and it's really about efficiency. So in the previous enhancement, I talked about performance through scalability. That's a very critical thing, and that's much like what we are doing is if you imagine you had a roadway and you have maybe you're treating performance a lot like how fast you move along the road with traffic. If you add another lane, obviously you can support more volume there and you can get faster the road. But the other option is to, if you're perhaps going to a particular place, have the road diverted directly to your work instead of having to make other go in other directions as well in order to get to where you're trying to get to. And that's really what this enhancement is. This is really about a specific, your problem and how it solves. We can improve that proficiency if you already know before it begins how that problem solves. So perhaps you know you do need small increments at the beginning, and then that can transition to large increments, and you can use that to really make an efficient solve while avoiding cutbacks. So that's one situation when you know how your problem is going to solve. The second situation is maybe you didn't know, you ran it initially. You now know how the problem is going to solve based on the incrementations that were successful in that, and bring those successful incrementations back into the next run that you might do, and avoid cutbacks, and maybe change the incrementation to maximize your or actually optimize your runtime. And finally, the flexibility it gives you, ease of use, just this control, this think of it as you are now really dictating on how the solution happens. But we still allow cutbacks, I'll say that. But there has been ways you could kind of get a similar effect of this. You can break your job up into different load cases. And that was, of course, very tedious and very difficult to do. And you really didn't transition, couldn't have a smooth transition from one increment size to another. And so this, if you were doing this older method, that's no longer needed, of course, because now you have that control. Just talk about the example engineering application. So post-buckled stiffened panels, which exhibit large number of cutbacks, is only one example. But really, this kind of graph kind of tells what the story in some regards of what we're trying to do. If you think of the path that you're trying to go through to find incrementation, when you first run it, sometimes it's a maze, sometimes it's a maze though where you already know how you need to change the incrementation. But sometimes you find for the first time, but then every other time after that, if you know the shortcut, if you know how to avoid these cutbacks, if you know how to go fast and when to go slow, you can really speed up the analyses. The implementation, we have a new option, and it prescribes a user-defined time step. You can see that down here in the lower left. We have this new user-defined time step with a table you enter. So what defines the increment size is the time stepping data. So this, where this first increment is, that time difference is your increment size. So you can see that I ran a couple large increments followed by a number of small increments in this particular example. We don't use the Y value currently. I do think that we are going to look forward to maybe a time where we might use that Y data, but at this time we don't. So you can adjust it to however you're most comfortable. We find that one best practice is to set it equal to the increment number so that you can see the increment number based on how you're changing things. There's also another way to set Y data. You can set it to the same as the x-axis as well. That kind of sometimes helps really highlight the differences in the increment size. So they don't show up artificially large or small based on your ratio of your plot. The automatic time step back can still be used, as I mentioned before. Probably should be used just so that if you do, especially if you're doing a priori and you are off a little bit, it'll still cut back without causing a significant amount of run cycles instead of aborting the analyses. So here's a couple of the other, we did a large number of test cases, of course, and we have a couple examples. We have some that are even shown that are up to even more faster than what we have, 5 times faster. But in the top, we have a post-buckle panel. You can see with the grid, with the color pattern, this is the buckle pattern that we got in the skin. And this was the actual table based on what we had done, work that was done before of the actual time stepping. So we can see that we were initially able to run fairly small number of increments of a fairly decent size, and then there was a transition period, and then we had to run very, very small increment sizes, a large number of them, and then we were able to actually even out again and have each increment with some respectable amount of load improvement. So throughout this thing, we actually reduced, we only took the increments that were successful. So any increment that resulted in an unsuccessful, where there was a cutback, was not included in here. And so this essentially is a roadmap of how you get this analysis last run got to convergence on every single increment. We reduced the number of iterations when we added it, when we drove in the analysis with this time stepping to 30% lower. We reduced the number of cutbacks by 80%, and we got a speed up factor of 1.4. The only thing I'll note here is we did not completely eliminate the cutbacks, and we would have gotten more speed up factors potentially if we had done it. What we didn't do is eliminate the cutback increments. We kept the standard increments that were used for load cases before and after the load case that we did describe with the table. We did that because, of course, we have to test to make sure that it's compatible. If you chain load cases together that we're using different incrementation, whether it is user-defined time stepping or with fixed and or adaptive. So you have to be able to, we want to make sure you're able to combine those, so we make sure we test for stuff like that. The other model is something that unfortunately happens for us in the sense that we can't show you exactly what we tested. It's a proprietary model that was shared with us for testing purposes. But we maintain our confidence from our customers and keeping what they want us to keep proprietary, keep it proprietary. But the stories that the results show are very important. So this will come up from time to time. These are also, when you see proprietary model, you can almost be assured that this is an actual model that you might run. It's a real world model in every sense of the word. And you can see there was a ramp up. There's initially a little bit of a fast ramp up, a number of smaller increments followed by regular size, and then we got to very, very small increment sizes. Based on what we're representing here, if you have a very steep curve, it means you're taking very, very small increment sizes because the time difference is very small. So we had obviously a very highly nonlinear event here, and maybe a smaller nonlinear event in the beginning. In this case, we reduced the number of iterations by 75%, which was a very large amount. We reduced our cutbacks by 100%, so we no longer had cutbacks, and reduced the speed, and the speed up factor was about 4.28x. In all these cases, sometimes we would make small modifications to the model, and sometimes we just tested without, just to test some of the extremes. So in some cases, there are a chance that you will still have some cutbacks because your change could result in some overall behavior of the model. But this functionality is really at its most beneficial when you have a good idea of how the model is going to converge. The third category in Smarter Solve is the enhanced contact parameters. We think a number of customers are going to be quite excited by these. We did some things regarding ease of use, particularly around low-controlled contact bodies. Before, you used to have to use two nodes, one for translations and one for rotations, to define the loading on that low-controlled contact bodies. Now it's a single node, and I'll explain a little bit more about that when we talk about the implementation. But that getting rid of two nodes and going to a single node is much more intuitive, and it's also much more easier to deal with when you're defining your model. From a robustness point of view, we have a contact tolerance is now calculated on a per body pair basis. So if you're familiar with contact tolerance, that is really kind of the distance at which it determines that you actually have contact take place. and it was done on a global basis, which means that if you needed a small contact body, a small contact tolerance on particular bodies, but a larger one was better for other bodies based on the Marc default calculation, you got stuck with one or the other. In this situation, now it will calculate on a per body pair basis. And then the third one is also an ease of use, which is that contact tolerance, even when you do it on a per body pair basis or not, and also the contact penalty factor if you're using segment to segment. Scaling that was something that is sometimes needed because you had too much penetration and you were not able to converge or you didn't like the results as it was because of that. And people would have to go through a fairly lengthy process, somewhat tedious process to come up with a more stiffer or less stiff penalty factor, depending on what they wanted. And so now we just allow you to directly say whatever Marc calculates, I want you to scale it by some factor. And it's very quick and very easy to do that. So example engineering application as kind of suits all of these smarter solve enhancements. Anything, in this case, obviously, if you're using low controlled contact bodies, this is very valuable. But then large variation mesh sizes or convergence issues due to excessive penetration, very stiff penalty factors. Anytime you're using segment to segment in particular, these can be particularly valuable enhancements to you. The implementation for a single control node is up on top. Before I talk about what we did, I will say the previous method, which used an auxiliary node, is deprecated. And so now you just have the single node. By default, the rotation is suppressed. And that is because we knew not everyone was working with 6 degrees of freedom, and we didn't want to introduce them to the system if they weren't necessary. But that's easily fixed by changing it to allowed, in which case now you have all 6 degrees of freedom on a single control node. The contact distance tolerance, you can see typically this was not a drop down. This was just global. This didn't even exist in the previous release. It was just global. Now we've added the per body pair option, and then also you can scale the factor here. You can see if I want a little more contact tolerance, then I can increase that value or decrease it using a fractor. And then the contact penalty factor as well. As I mentioned, you can now scale it. If you scale it in the normal behavior, it's a scale factor that's applied to every body pair. But especially with contact penalty factor, we knew that people sometimes it's just a single body pair they have to adjust. So now you can do it on a per body pair basis as well in terms of the contact penalty factor. So that's, you can see in both cases, we're trying to do things that deal with the variations that people see in their real models. The use case, again, the proprietary model box comes up, but it's easy for me to describe really. Imagine you are going to preload a stack up with a bolt and a nut, and you're going to preload it, and you have some kind of stack up in between. That's essentially what we were doing in this proprietary model. There was an initial run with smaller increments. There are 42 increments with, of course, the torque increasing with all the default settings for contact. I will mention in a reply back to the user-defined time stepping is 42 because this was a situation where when I was first investigating the problem, again, I wanted to ease into the contact just to make sure I didn't have any issues and I could really track what was happening down and the results as well. But with everything, when you're running these kind of analysis, in this case, there's maybe a large number of stack ups that we want to look at. There's a lot of different bulk opportunities for us to work with. There's a desire to decrease the runtime, so we could run a large number of these. And one of the common ways of doing that is to increase the increment size. Now, just a word of caution that this is the first thought that everyone has, and it's a good thought, but sometimes you do have to be careful because decreasing the runtime or by making increments larger can simply result in more iterations in the larger increments, and that can really take away some of the benefit. I won't say that's a regular occurrence, but just keep in mind that is possible, that not every time increasing increment size directly translates into faster analysis. In fact, pretty much every analysis will have some point at which that transition happens to even going to larger increments does not necessarily happen in a faster analysis. But because we actually had too much penetration, if you think about the threads of a bolt turning into the nuts of a thread as you're rotating it, as you're applying the torque, the more you torque it, the more you rotate it, the more penetration that will happen. And so, understanding the mechanics of any problem is very important when you're doing simulation. We saw that, and the first thought that came to the mind is let's increase the contact tolerance and the penalty factor. And when we did that, we got a run of 20 increments, and it reduced the run time by 40%. So here's a situation where we did get a real improvement, and you can see some of the results. We started having some plasticity, significant plasticity took place. You can see where it starts deviating on the two simulations versus the theory, but we had good agreement with the theory. And then we had good agreements between the small increment with all the faults, and then a lower number of just 20 increments with a little bit higher tolerances. So 40% is a great improvement if you're going to be running a large number of these. And the fourth and final improvement in the smarter solve is the point cloud data mapping for the global remeshing. So this is one of the enhancements. If you're doing global remeshing, we'll make sure we're reaching out on this with our any local presentation. You might have this from your AE as well, because it is the new default method. We found that just the accuracy in many places was causing issues also that were misattributed to just the fact we weren't converging, and instead perhaps the results were not as accurate as we would have liked in the remapping, rezoning, but also people were seeing excessive smoothing in the results, particularly for large gradients or single Gauss point elements. Obviously, we're going to talk a little later about a new single Gauss point element, but the smoothing resulted in significant deviation enough that we wanted to take a look at what we could do to get rid of that in some cases. And so this new method came up. So example engineering application, it's really appropriate for any time you're using global remeshing. That's usually with simulations with large distortions and or large gradients in the results. That tends to be where we tend to see the greatest need for global remeshing. Of course, that tends to happen particularly with metal forming or high plasticity events, and hyperelastic performance in many cases has a large amount of deformation and gradients. If we look at the implementation, I'm going to just kind of talk you through it. It is the new default, as I mentioned again. I apologize if I'm being repetitious with stuff like that, but we do think it's very important that we do our best to make sure you're aware of that. So it will likely cause some differences in the results of using a previous analysis that's using remeshing. Due to that lower amount of smoothing, they'll be more accurate. But we know in some cases people love the accuracy, but they really need to stay consistent for some time. So the older method is still available, and it can be requested. We still have availability of that older option, the older method we use. To talk through how the rezoning, the remapping of the results takes place in Marc. We're really going from integration to integration points. That's the big difference in the new method. We create a point cloud of the old mesh integration points, and that's mapped to the new mesh integration points interpolated. So in this case, we're not going through any nodal calculation to do it. We're going straight from integration points to integration points, and that's what enables a large amount of our accuracy. For nodal data, we actually have another point cloud that's just based on the nodal locations, and we map from the old to the new, and we do it by closest distance for the nodal data now. This is also very important in many cases for also maintaining the accuracy and the results in the previous mesh to the new mesh. The one issue in there that we know could have come into trouble is at the boundary. You have to make sure that when you're doing your mapping, that you are not mapping to a node that's inside the body, and you're only using nodes that are out on the outer peripheral of the boundary, because we can get a incorrect result that way. So we only use boundary nodes to boundary nodes when we're doing nodal values at the boundary. The use case we have, we're showing here, is just a simple remeshing of a plate with a hole. You can see the model here. We loaded it up, and we have a stress concentration, as you might expect. And you can see we have a very high gradient. This is the original result. With the previous mapping, this was our biggest concern, is that you do have the risk of losing that high peak because of the way we calculated before. And with the new point cloud mapping, this is our new functionality down here at the bottom, we retain that large gradient, and we get some really good results. You can look at it a different way. We've extracted some results in different parts of the analyses, and actually at a sample point over time, and you can see that with the brown, which is the original mesh, and then if we remeshed with blue, and then we remeshed with the older method in red, that the new method remeshing with the original mesh was much more accurate than using the previous method. So I kind of gave us a quick preview there. So those are the smarter solve improvements. They're very, I think, applicable to a wide range of analyses. So please take a look at them. Let us know what you think. I'll move next to the second category, which is the GUI improvements. So this really, in this release, a lot of what we did here was on the enhancements to the look and feel in Mentat. There's really there's really four, even though I showed three bullet points, and I'll explain that in a minute. But the first thing that I'll talk about is the dark theme. So these dark themes are becoming very popular. If you have the latest installation of Windows 10, they have dark themes. Microsoft actually has dark themes that you can use across their Office 365 applications, Word, Excel, PowerPoint, things like that in terms of the user interface. Also, there are dark themes. iOS has introduced them. Android has had them for the same time. So we know they're very popular. Anecdotally, we hear feedback from both internally, including myself and others, that there is a feeling of a difference that is noticeable enough that you enjoy working with a dark theme at times, because it does feel easier on the eyes. But there's also, I think, a movement to dark themes as well in general. We have new mouse options when you're panning, zooming, and rotate. Really, what it comes down to is today you'll use the keyboard shortcuts, or you can obviously use the icons. I think for some people, they're familiar with that and it works. But when we look at what we've done in what's been done in CAD, what we've done in products of our own, like MSC Apex, we knew that the idea of just using the mouse to do that without having to enter into a mode repeatedly is a huge improvement for many people. So we have these new options where you're able to do those kind of operations with the mouse without having to engage a mode constantly. And then finally, we have an option to select entities partially in the selection box. Previously, it had to be completely in the selection that you might do, and now if you can define it so that if it contacts or crosses across the selection box, it'll also be selected. There's an example in the video I'm going to show in just a minute that will maybe make that clear if my description was a little confusing. And then there's an option to automatically create a selection without using end of list. This is actually a very, also another very good capability. When you see it in action, that's when you really realize how much faster and easier it is to build selections, whether it's just a single thing or whether it's requires multiple manipulations to define the elements or nodes or whatever it is that you need to select. And that's an ease of use improvement as well. So example engineering application. This is a kind of a callback to the other one. Anytime you have Mentat and you're interacting with Mentat, you can have these on. As we'll see, these are always options. You know, we're very careful to make sure that the people who are being very productive in Mentat can stay that way. And so we make sure that these are introduced in a way that's easy to turn them on or off, but also to retain the traditional look if that's what you approve or if that's what you prefer. So the implementation, you'll now see in the top window, there's going to be a mode. And what we've done is the changes that we've made regarding the things that we have new options for. We have a preset that basically this could boil down to this is the traditional way, the way Mentat works and has been working. And then we have the second preset, and this contains all the changes that we've done. But you're not limited to just the preset 1 and 2. If you go to these settings, you can see you can also change the preset this way, but then you can change the individual things. So you don't have to take all the changes at once. You can do them individually. As you'll see a little bit in the text of the implementation, there are options other than this mode setting in other areas where you might be more used to making the change, and we allow that there as well. The first thing you can set, if you were to set things individually, is the theme, whether it's traditional, which is the light theme, or the dark theme. This was, I think, important for us to separate out. We know that even if you do like working with a dark theme, when it comes time to write a report or clip an image for sending off, the dark theme is not always the most conducive to a report in terms of readability. So you could easily switch to a light theme, take your snapshot, and then switch back to the dark theme after you've done that. You can also save the settings for these things individually to the ini file. So every time that you open it up, it's set up that way. Again, you don't have to do the presets that way. You can just do each of the individual functionalities. The mouse view manipulation, this one is definitely best shown during the video that I'm going to start with, but you can see that they have the traditional and what we're calling the autodynamic mode. This is where you're more dynamic with the mouse and how you're interacting with the viewport in terms of panning and zooming and rotating. And then we have this picking mode, where again the default traditional has always been to the left with complete, but we've introduced this partial picking. Finally, we have a new Thunderbolt icon on the list specification group. What this does is allow you to set the behavior when it's on, that whatever you select, it'll automatically and instantly add it to your selection without having to end of list. And it allows you to build things maybe in a more a way that can feel much more fast to people and less worried about making mistakes than having to recover from them. So I'm going to show you a video. I apologize, I have to get out of pointer mode to do it, and hopefully I'm able to click on this correctly. Sometimes I accidentally click and I go to the next slide before the video is done. I have a number of stops. So I started off here by just kind of, you can see the pointer comes down, unclicks the hand, and then I was trying to just replicate my own frustration where I forgot I turned off the hand and I was trying to manipulate the image and I couldn't do it because I had turned off the hand and I was not using keyboard shortcuts. I moved back up to the mode, and now I'm going to show you the mode menu and how to switch between, how the switch works. This is preset 1. I can go to preset 2. If I go to preset 2, I'm going to switch to the dark mode. It's actually interesting, so if you walk at the screen now, maybe you will see the similar effect, maybe you won't. But it's very bright right now. There's a fair amount of, depending on your monitor settings, of course. When the video starts again, I will actually switch to the dark mode. So for me, there's somewhat of a weavement of the eye strain. You can switch back to the preset 1 as easily as just clicking. I'm going to open up the settings in there instead, and we can see that we'll switch with we have the same presets as we had above. You get some tooltip help there, but you can switch. You can see that when I switch it, this yellow mark on the left will light up and tell me what mode I'm in case I didn't know. If you had watched in the video, maybe I'll go back and remind you now. If you look, the settings here below will switch from the left to the right whenever I go from one preset to another preset. So now I will actually, we'll go ahead and look at the dark theme settings specifically. So I switch to the dark. It's only the dark that's changed, nothing else has changed. And again, I can save and restore those settings. When I'm working in the dark menu too, note we're really trying to work on the contrast. We've had a couple iterations. We think we're in a good place, but feedback on the contrast that you might see in the dark menu is very important to us. So please let us know about contrast when you're navigating within menus and highlighting, etc. From the interface perspective. Let me go on to the next one where I'm going to actually show what I'm doing. So I turn on aerodynamic. I didn't do anything else. Until I turn off that aerodynamic, I'm able to manipulate the viewpoint using the mouse and do this without hovering about any hand icon or anything. And again, you can save and restore to make sure that every time you start, if you want aerodynamic, it will start that way by default. The picking, of course, is really, I'm going to create a selection here. I apologize if I'm going to go a little bit fast in the video. Sometimes I forget how I need to talk and show people what they're doing while the video is running. But what I'm going to do here, this is not on. There'll be a different image of this when it's actually activated. I'm going to go ahead and just do things the traditional way with complete. So I'm just going to show you the traditional way that maybe I would add some elements. I'm going to select them. I'm going to box only everything within that box is selected, and I have to end of list. I have to do the end of list to have it show up. There are 320 elements. And I quickly cleared them away because I was in a hurry to show you the new capabilities that we have. So I'm going to come on, and now I'm going to turn it on. And I select that, and it's automatically added. Again, I did it a little fast, but I had 320 elements added almost immediately. No end of list. You can see that if I want to keep adding, or do some other action, it's easy because I don't have to do the end of list. When you're only doing one, maybe it's not as big of a savings, but when you do this regularly over and over again, and your selection is a complicated one to build, it can really significantly improve your ease of use and reduce your time. I'm going to show next, I'm going to show you the partial. So I'm going to click down, let me do this, I'm going to go turn on the partial, leave on the autocomplete. I'm going to select the elements before, which was only one kind of, one of these axial segments, and now, or sorry, one of these segments, and then now we got two of those segments, and we got 640 elements. So these functionalities in I think Mentat show how we're really starting to again pay attention to the ease of use. These are things that everyone will experience on a regular basis, and of course, in addition to this, one of the important things about Mentat is the 100% support for the solver. So all of the improvements you saw before and all the improvements you're going to see after on the solver side have all in the GUI for you to interact with. And I think that does it for my section. And I'll hand it over to Bhumi to do the use case improvements and let her take over.
Section, we're going to talk about the use case improvement, which are more workflow specific improvements we have done in this release. So if you can go to the next slide, please, Matthew. Okay, so the first one is the Vegter anisotropic plasticity use criteria. This is an addition, this is the new anisotropic plasticity model, which has been added. And this is mainly driven by our manufacturing industry users. And the main benefit of this is that it improves the ease of use in calculating the yield criteria for anisotropic plasticity. There are three ways to calculate the yield criteria. The first one being the parameters are provided by the material suppliers, such as Tata Steel. We have worked closely with Professor Vegter in Netherlands, or you can call Aurora Online, who supplies the material and provides the ready-to-run input decks. So these material files are contained, they contain all the required material data on a specific grade and can be directly used within Marc to run forming and crashworthiness simulations. So if you're using their products, it is very easy to get the data into Marc. Secondly, you can calculate the parameters obtained from experimental uniaxial, equibiaxial, plane strain, tensile, and shear test. This is what we call the Vegter standard in 3, 5, or 7 directions. And then the last method is that one or more intriguing aspects of it is that in 2017 there are some papers published which shows that this criteria works in parameters that you derive only from uniaxial test data in 3 different orientations. And this is called the Vegter 2017. So this can greatly simplify the defining the behavior for the yield criteria. The main engineering application of this criteria is the sheet metal forming simulations. So next we will go through the implementation of this criterion. So the implementation is very straightforward. So now when you go to go and turn on your plasticity, you can say your yield criterion and you have an option to select the Vegter standard and Vegter 2017. In this case, you can set the number of angles that you need to define, and that will change the table size accordingly. And if you select Vegter 2017, it is much more simplified simulation. Please ignore these numbers in the 2017 table. They're just random numbers that we have included just for the purpose of taking pictures, but you can enter your numbers accordingly. So if you go to the next slide, please. Next, we'll talk about the use case for this criterion. Here is a test case on the cup drawing model. We use a Hill model, Bartlett model, and a Vegter standard 3-direction model. You can see that this initially started off as a flat disk and then turned into a cup shape. We looked around the edge and looked at the peaks and the valleys, and we have pretty good agreement, especially between the Vegter and the Bartlett model. And we also looked at the values at 3 nodes in the radial direction, and we got pretty good agreement over there as well. So if you do this kind of work, you have another, or if you have any other type of work that can use an isotropic yield criterion, you can explore the Vegter option now with Marc 2019 Feature Pack 1 release. Next, a workflow specific enhancement that we did was dual frequency induction heating. Induction heating is something we have been working on since multiple releases. In this release, we expanded our range of capabilities from simulation of these type of processes by adding dual frequencies. The reason we added dual frequency is that when you have a complex part shape and you have variable distance on the outside edge, it can really benefit to use multiple frequencies, as the frequencies can dictate the temperature and heat pattern on the part based on the distance set by the frequencies. So the most common application for this is the gears. So if you have surface hardening of the gears with induction heating process, dual frequency definition can be extremely helpful. So next we will talk about the implementation of this workflow specific enhancement. It's pretty when you're using using appropriate load cases. For that, you now have an option for not only using the single frequency, but also dual frequency. And then you can assign your high and low frequencies. High frequencies need to be in the multiples of low frequency. This is a rule for defining the high frequencies. It will make the adjustment for you in Marc. So it is really important that you set the high frequency as the multiple of the low frequencies, so you get out what you are expecting. And only the high frequency results are outputted in this option. So you're not going to see the low frequency results, only the high frequency. So, but for the case of current density and generated heat, you will get the sum of two frequencies. So it's combined results in that case when you have even when it says high frequency over there. So next, we will go to the use case scenario for this one. Our use case for this is, of course, we did use a gear tooth and the tip of the gear. So on the left here, you can see the limitations of single frequency for both low frequency and high frequency. We're getting either the root or the tip of the gear heated. But what we really want is a uniform scenario. So by introducing the dual frequency, we're getting this more uniform heat pattern, and that helps with the phase transformation that we're going to see to be more uniform as well. If you're doing induction heating, whether it is gears or anything else that has potential for dual frequency, you can save a lot of time with this new capability before you invest in your hardwares for it or invest towards the experimental testing. Now the next enhancement is the single Gauss point tetrahedral Herrmann element. So as Matthew would, this could also belong to the smart solver as well as the workflow. So Matthew and we were talking about it, and it depends on how you use it, but it could belong in both the criteria. So anytime we introduce reduced integration, it tends to improve everything associated with that. We know that Herrmann element is very popular in the rubber, in a lot of rubber and a lot of metal forming application. So I wanted to highlight that here. And then if you have a situation where you have incompressible or nearly incompressible application and you're using Herrmann elements that we have today, you can now use a reduced order integration element. So when you use the lower order element, besides the speed improvement, you also see the improved robustness because that center bubble node sometimes move outside the element with the full integration element. And that can cause exit 1009 error, the element going inside out in some simulations. So single Gauss point element eliminates that problem for you. The applications for this element would be in any simulation with large strain rubber behavior or large scale plasticity, usually manufacturing, forming, and rubber elastomer type of applications. So next we will go to the implementation of this element. This is a new element, so Matthew would like to say that we're going to have a birthday party for this element. It's element type 247. We're introducing
Happy birthday, element.
Yeah. So happy birthday, element 247, right? So we're This is a completely new element, and of course, it is a four-noded element, linear displacement plus linear pressure field, because of the single Gauss point integration. We also added hourglass stabilization for the pressure degree of freedom for this one. So next we will look at the use case scenarios for this one. So we did perform. We're showing here two use cases, but we did perform a lot of tests. Some of them are proprietary models; they're not shown here, and we have seen up to 50% improvements in the wall time. So if you look at the first test here, we had 38%, and in the second one we had 37% improvements in the runtime. And we compared the run against the simulation with type 157, and then we ran the type 247, which is the new element. Yeah. So next one, we have the shape memory alloy enhancement. This is the last enhancement I'm going to talk about. We have a new option to specify different tensile and compressive behavior in thermomechanical shape memory model type 2. During the transformation of Augustine Martensite and Martensite-Augustine, to be able to specify different tensile and compressive behavior under tension and compression is a major addition. It will help the accuracy by simulating this behavior. Also, we're now supporting the isotropic hardening at the higher load levels after the transformation of Martensite is complete. This further improves the accuracy by extending the simulation beyond current limits. The example engineering application for this would be, the most common for this would be that the type, the stents mainly, anywhere you're using the shape and memory alloys would help. Next, we have the implementation of this, which is quite straightforward. When you look at the menu, you can see that you have options to set alpha and beta for configuration, configuring the plasticity behavior during the transformation during tension and compression. Now you have the table for Martensite where you can define the isotropic hardening, the fully Martensite case as well. So if you go to the next one, we have the use case scenario for this one. Here is the example of this, and you can see that the tension and compression are right on top of each other, and it follows this red line. So that is with the default alpha and beta set to 0. And then, depending upon what you believe your correct shape for what is correct for your shape memory, or or what you get from the test data, you can vary your alpha and beta. In this case, we are varying only alpha. We have examples where we have varied only beta and also the alpha and beta both, and you can see that you have remarkably different behavior in tension, which is shown in brown, and compression, which is shown in green over here. And we get some of the hardening of Martensite equation, as well as once it's fully being converted as well. So if you go to the next slide, please. So that's the end of the enhancements that we have done in this release. For more information, you can go to the What's New in March 2019 Feature Pack 1 from your Help What's New, and you can also refer to the March 2019 Feature Pack 1 release guide. And if you go to the next slide, we have now opened the poll for questions. So if you have any questions, please type them in the Q&A panel, and we will address them right now. I would also like to encourage everyone to please fill out the poll for this webinar. And also we have Audrey on the line, who is our development head for Marc. He can, if you have any questions, he will also help answer them to us today. A recording of this webinar will also be posted on our YouTube channel, so keep an eye out for that if you would like to share it with your colleagues. Okay, I do see one question. How can we deal with STL file in Marc? So Matthew, do you want to answer that?
Yeah, maybe Audrey could talk to that. This is a question that comes up quite a bit. Is there more context for it, or is it just how do you deal with STL files in general?
Yes, in Mentat we have the possibility to import such files, and they can be imported as geometry. And you, for instance, can use them to model rigid bodies, or for instance, closed surface to do meshing operations on. So there is a possibility to import them and yeah, and use them.
Okay. Thank you. If you have any other questions, please type in the Q&A panel. I do have a question sent out to me privately. Is Marc 2019 Feature Pack 1 available to download? Yes, it is. You should have gotten an email last Friday. And if you go to our download center, you can download it today. We have one follow-up question to the STL question. How can we apply boundary condition on STL file mesh system? So, Audrey, would you like to answer that right now, or we can follow up with the user after the webinar as well?
Yeah, we can do it, say, after the webinar if we have more details, but say it's if it has been meshed, say boundary conditions can be applied to the finite element mesh. If it's say still geometry based, we also have options to apply the boundary conditions to the geometry, and later on when it has been meshed, it will be associated with the mesh. So there are different options available.
Okay, great. Sure. The next question is, can we download trial version of it? Yes, absolutely. Please send an email to me and I will set up a trial version for you today. So we have the email in the next slide. So just if Matthew, you can go to the next slide, they can note down the email as well. Yeah. So just send an email to either me or Matthew, and we can set up a free trial version for you to explore more. Okay, looks like I do not have any new questions coming in. Thank you everybody for your time today. Thank you, Matthew, for your wonderful presentation. Thank you, Audrey, for helping us with all the questions. And we will post a recording, as I said earlier, and have a wonderful day and evening, depending on where you are. Thank you. Bye.
Thank you, everyone.